So to the last section of this short chapter on introduction to initial value and boundary value problems, we looked at the direct numerical solution and said we ended up with massive system matrix that has to be inverted, and then we went to iterative methods where we take the time derivative and then drive towards equilibrium solutions, and we looked at the Jacobi method and the Gauss-Seidel method, and we said Jacobi is quite slow in converging. Gauss-Seidel speeds it up, but still not fast enough. So there are other methods like method of successive over relaxation, often referred to as SOR methods, where we are again going to write the numerical discretization of the Poisson equation as Ci plus 1j plus Ci minus 1j plus Cij plus 1 plus Cij minus 1 minus 4 Cij equal delta x squared rho ij, where we assume that delta x is delta y, and the solution at ij depends on the source sink term and the neighbors, and we had decided to number the all the grid points from 1 to n times m. So we have 3 by 3 system, so it goes to instead of 1 1 1 2 1 3 and 1 1 2 1 3 1 and so on, to C1 C2 C3 to C9. This is what gave us the matrix. So now taking C to be X, just to go back to the matrix representation of the system, we write it as AX equal B. So X is what we had been talking about as C. So here A, remember we ended up with a block matrix, so it can be written as a diagonal term, a left and right blocks, and off diagonal blocks basically. So for the Jacobi method, then we ended up writing the equation as d times x to the n plus 1 equal minus L plus R at xn plus b, and the Gauss-Seidel method changed it by using the previously solved for terms. So we got d plus L times x to the n x at n plus 1, so still writing our solution for n plus 1 to drive towards equilibrium solution, equal to minus r xn plus b. So this accelerated the convergence compared to the Jacobi method, but there is a way to accelerate these further by writing this this equation as x at n plus 1 equal to x at n. You can think of n as iteration now instead of time, for example, minus d plus the left block to the minus 1, which is the inverse. So remember, these are matrices, so we are inverting here, times d plus L plus R to the times xn minus b. So this is our A. So this is basically A at xn minus b, which is the same as our solution, same as our original equation. So essentially that means x at iteration n plus 1 is x at iteration n minus axb. Hence that is basically a this is basically a residual. Okay, so you can write then the solution as x at n plus 1 equal to x at n minus d plus L inverse times the residual, which is like a correction term we are adding to the previous solution. So iteration n give us a solution, you add a correction to get the next iteration. So what we can do is then multiply this correction term with a w, which ranges from 1 to 2, so 1 less than w less than 2. If you make that 1, obviously you get the Gauss-Seidel, but you can choose a omega, not W, omega as an optimal parameter, which is tricky, but you can find it, as we will see, by searching for your particular system. So x at n plus 1 is x equal to x at n minus omega times d plus L inverse times the residual. So if you have the optimal omega, it turns out that you can accelerate the convergence. So previously we said it can be shown that in order to reduce the error by a factor of 10 to the p, here only 1/3 p times j iterations are required. Obviously, this is much cheaper than what we had before. The computational burden, therefore, only scales linearly with j, the number of grid points, rather than quadratically as we had before. Before we had 1/2 p to the j squared for Jacobi and Gauss-Seidel methods. However, this only holds if an optimum value of omega is used in 5.22. So that's the tricky part. There's never any free lunch. And this is the difficulty in the successive over-relaxation methods. Luckily, there are some prior estimate for omega optimum. You can see these papers, the book for a chapter on relaxation method. For smaller problems, omega optimum can be found by a search algorithm. Well, I'm not going to go into those details, but you get the point that successive or relaxation methods reduce the iteration to this with omega as an optimum parameter that can multiply the correction term to the previous solution, previous iteration to give you. But in practice, this looks complicated. In practice, it is simply written as aij times x at I plus 1j plus b at ij x I minus 1j plus cij x ij plus 1 dij at x I j minus 1 plus eij at x I and j equal to f I and j, which is the right hand term. So here x at ij and n plus 1 iteration n plus 1 at grid point I and j is the previous iteration at I and j minus omega times zeta ij at iteration n divided by eij. So zeta nij, which is the residual here, is then equal to aij at xi plus 1j in iteration n plus bij xi minus 1j at n plus cij xij plus 1 at n plus dij xij minus 1 at n plus eij x at ij and n minus fij. So now you have the idea of how methods of successive over-relaxation work and what are the difficulties in doing that. So you do accomplish computational efficiency by accelerating the convergence, but the optimal parameter has to be found, which is easier for shorter, smaller problems, smaller grid sizes and so on, smaller domains, where a search algorithm can be used to do that. But for bigger problems, that is the tricky part. Okay, so you gain something if you can find an omega, but finding the omega itself has to be a real saving over the Jacobi method and the Gauss-Seidel method. Okay, that's the tricky part. But as you can imagine, as j grid size increases in Jacobi and Gauss-Seidel, the convergence only goes up as 1/2 p j squared. So the problem is quite heavy as the grid gets bigger. So there are some pros and cons of using these methods. So in the next chapter we are moving to large-scale ocean circulation. So we touch on how to add the Coriolis effect, which is very critical for the climate problem, and then we will see what simplifications are done to derive things like the shallow water model, and then see how solutions to that simplified model can be found. Okay.